Part 7. When a stationary wave is formed, when two waves of equal amplitude, equal frequency, equal wavelength, equal speed, moving in opposite direction, superimposed with each other, a stationary wave is formed. So what is the equation of a stationary wave? Already we derived this in the previous class. Y is equal to 2a cos kx sin omega t, or one more equation, y is equal to 2a sin kx cos omega t. Okay, minus. Here, if you observe this one, students, the amplitude of this stationary wave, this amplitude depends on x. We will see if amplitude is A, resultant amplitude of stationary wave is given by, I am writing AR, resultant amplitude or amplitude of the stationary wave is 2A cos kx, 2A cos kx. This is the amplitude of the stationary wave. This amplitude can be maximum, can be minimum. Can be maximum, can be minimum, or it can take any value. We will see how this amplitude changes. How this amplitude changes. Now, in this case, if amplitude is given as 2a cos kx, the resultant amplitude depends on not 2a, because 2 already constant, a already constant. It depends on cos kx. Which value? It is cos theta only. What is this? It must be theta. Kx. Okay. So this is kx. So amplitude depends on cos kx. If cos kx, what is the maximum value of sin theta? Sin 91. Minimum value of sin theta? Minus 1. If you take the magnitude, plus a and minus a. But if you only take without sin, if you take maximum minima, sin maximum value 1, minimum value 0. Maximum value 1, minimum value 0. Here similarly cos maximum value 1, minimum value 0. If cos kx is equal to 1, cos kx is equal to how much? How much? Cos kx is equal to 1. When it is possible, when cos kx will be 1, we can write cos kx is equal cos 0, correct? What is cos 0 degrees? And here we can write cos 0 radians also, or cos pi, cos pi minus 1, but I am taking only the mod of cos kx, cos 0, cos pi, cos 2 pi, cos 3 pi, and so on. So at these points, this value will become maximum. So what is cos kx now? This one, if you take only kx, so what is kx value? Just to compare this cos, we remove it. Remove this cos. Then what will get? 0, pi radians, 2 pi, 3 pi and so on, n pi, where n is equal to 0, 1, 2, 3, 4 and so on, where n is equal to 0, 1, 2, 3 and so on. This is kx, this is angle, kx is angle. What is k, students? 2 pi by lambda. What is k? 2 pi by lambda into x is equal to 0, pi, 2 pi, 3 pi and so on. So what is x? 0 into 2 pi by lambda will become lambda by 2 pi. How much it is? You just bring this 2 pi by lambda this side, students. Lambda by 2 pi into 0, how much? 0. Lambda by 2 pi into pi. Pi into, if you bring this value this side, what will get? Lambda by, next, 2 pi into lambda by 2 pi. 3 pi into lambda by 2 pi and so on. So where you will get the maximum amplitude. I am finding where this amplitude will be maximum. Where this amplitude can be maximum. For this to become maximum, this value must be maximum. So I am taking maximum value. What is cos x1? This is a condition for maximum amplitude. Condition for maximum amplitude. So I am finding maximum amplitude. Can I cancel this 2 pi and 2 pi? This pi and pi. So what are the x values where this amplitude will become maximum? X value. Where you will get this x value maximum? Where you will get x value maximum? I am writing that x value maximum. X is equal to first value 0, second value this pi cancel lambda by, then 2 lambda, 0, 0.5 lambda, 1 lambda, 1.5 lambda, 2 lambda, 2.5 lambda, 3 lambda and so on. Understood? So these are the values. Now these are the values where what happens at these values? At these values, amplitude of the station wave will become maximum. The amplitude will become maximum. Now I will draw the stationary wave. This is the stationary wave which is traveling like this. This is a first wave, y1. What is the second wave here? Wave coming in the opposite directions. This is second one. This is y2. What is this? Now these are fixed between these two ends. Fixed between these two ends. Okay? Fixed between these two ends, and the wave is traveling only between these 2 points. This is not a progressive wave. This is a stationary. Energy transport takes place only between these 2 points. This wave won't go that side. This wave won't go that side. Fixed, stationary. That's what these are called. Stationary waves or standing waves. Progressive wave, once it started source, it continues to move and never comes back onto the source. But here, it is starting here, ding ding ding, and then coming back to the same source. That's what is called a stationary wave. Which way? Now we are going to find out where this amplitude will become maximum. Where this amplitude will become maximum. For example, if we take this one here, let us say this is the waveform. This is stationary wave. So here, from this can I take x is equal to 0? This is x-axis. X is equal to 0. So what happened here? x0, what happened? Amplitude maximum. Amplitude? Then once again, this is amplitude maximum. This amplitude maximum. This amplitude maximum. This amplitude maximum. This amplitude maximum. Correct? So at these points amplitudes are maximum amplitudes. Maximum amplitudes. At the same time students, the same condition I am taking here. If amplitude is equal to 2a cos kx is minimum. Is ಆಗಬಹುದಾ ಕಾಣಿಸ್ತಾ ಇದೆ. Here amplitude is minimum, 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 minimum. So there are some points where amplitude is maximum. There are some points amplitude is minimum or zero. So when this amplitude will become zero, see the diagram and tell me. When this amplitude will become zero, so this must become zero. So for this to happen, what is the condition? Cos kx should be, what is minimum value of cos theta? Cos kx is equal 0. Here maximum value cos kx is equal to 1. Here minimum value cos kx must be 0. So 0 is the minimum value or not? This is minimum amplitude. Minimum amplitude. So when you will get this minimum amplitude from this statement, we will see. Cos kx is equal to cos 90. What is cos 90? How much? 0. Cos 3 pi by 2. Cos 270. 0. Cos 5 pi by 2. 0. Cos and so on. These are the cosine values where the magnitude will become 0. Now take this cos on both sides. So what is the condition now? Kx is equal pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2 and so on. But what is k? X is equal to pi by 2, 3 pi by 2, 5 pi by 2. So now I am writing, see this pi get cancels. Then what is that x value? What is that x value? X is equal to how much? 2 by lambda comes this side. Lambda by 2. So what will get here? Lambda by 4. This will become 3 lambda by 4, 5 lambda by 4, 7 lambda by 4 and so on. This is the x values. Which values? These are the x values where you will get minimum amplitude. These are the x values where you will get maximum amplitudes. These are called minimum amplitude. If you observe these two set students, this value exactly lies between these two. That is 0 lambda by 2. This 0 half lambda. This is quarter lambda. Where you can fix this value, where you can insert this value. Exactly you can insert it here. And where you can fix this value, mukkal lambda, here. Correct? Now see the diagram. Where you are getting minimum values lambda by 4 between these two. This is maximum, right? This is maximum. What is this? Minimum. What is this? Minimum. What is this? Minimum. What is this? Minimum. What is this? From here to here, what is this distance? Lambda by 4. How much? Lambda by 4. Next, it is 2. 3 lambda by, it is 2. 5 lambda by, this is 7 lambda by 4 and so on. These are the values where we get minimum amplitude. So here in a stationary wave, we are getting two types of points according to amplitude. In between, this is neither maximum nor minimum, correct? This is maximum amplitude, this is minimum amplitude. This is in between the maximum and the minimum amplitude. But we are talking about first maximum amplitude points and minimum amplitude points. And the points which are having maximum amplitude. What are these points? Maximum amplitude points are known as, are given one name, and these points which are having minimum amplitudes are given one more name. So the minimum amplitude means, what is that minimum value? What is that minimum value? 0. So 0 points, these are the 0 points, right? What are these? 0 points. So 0 points are given one name. These points are given some name, and those names these are called node. What are 0 or minimum amplitude points? Node. N-O-D-E. What is it? Nodes. This is a node, this is another node, this is another node, this is another node. These are called nodes. In a stationary wave, the points where amplitude becomes 0 or displacement becomes 0, where the particles will not oscillate at all. What is meant by amplitude 0? Throughout their life, they never oscillate. But in a progressive wave, all the particles execute SHM. But in a stationary wave, there are some points where they cannot oscillate in their entire life in a stationary wave, and those points are called node. Node. Now, in the same diagram, students, there are some points where amplitude is maximum. Antinode. These are called antinode points. So what is a node? What is a node? The point where the amplitude is 0, directly, minimum. What is a node? Amplitude is 0. What is antinode? Amplitude is in these station waves, we will discuss about producing station waves on a string first. Producing station waves. Where we are producing these station waves on a string? Example, veena, guitar, sitar. These are all musical instruments which are using the concept of production of station waves on a string. So first of all, taking a string fixed between two rigid supports. Let the length of the string, students, length of the string is, I will write here, let the length of the string is L. Original length of the string is L. Now, when the string is vibrated by holding the string at middle, and if I move it down, this is called plucking. If it is plucked, then this will start oscillating, correct? So this string will get this shape. If you leave it, if you press it and leave it, it will go like this. So now I will draw this with the same color, white one. So I am showing this in white color only. This is the actual length of the string, and the final length increases or decreases? Increases because of the tension. Yesterday while deriving the expression for potential energy per unit length of a wave, their dx length increased to dl. So here also length, while vibrating, length increases. And whether it remains there or comes down. Now the same thing can be seen here. ಅರ್ಥ ಆಗಿದಾ? And if you observe this one clearly, students, whether this portion of the string vibrates or not, no, because it is fixed. The string is fixed between the two ends. Only the middle portion will vibrate. Only the middle portion will vibrate. So this is not vibrating. This point is also not vibrating. But this point going up and coming down, correct? This point is up. This is going up and coming down. Going up, coming down. Correct? Can I say this is amplitude? Now, when the string is vibrating, students, always this point will have same amplitude or different amplitude? Same. This is the string. The middle portion always oscillates between two maximum values. But what about this one? It never vibrates. What about this end? Never vibrates. What about this point? This point? Whether it can go up to here? Say yes or no? No. It always goes up to this distance or comes to this distance. What about this point? This will go up to here and up to here only. It will not go beyond that amplitude. So different particles will have different amplitudes in station. Progressive wave, all particles vibrate similarly. Either is to height over is to height. But next it will get the chance to vibrate up to that maximum value. In the order, in the wave, this particle rises up to here, this one here, this one here, this one here. So shape is a wave. Next, this will go down, this will go up. Correct? This will go up, this will go up. Shape changes. Wave. In a traveling or stationary wave. Traveling or progressive wave. Traveling or each and every particle will have same amplitude. Same amplitude. See, when I am drawing a wave like this particle now vibrates up to here. Whether it vibrates only this much or next it may go up. It may go up. It can go up to here. But the maximum value is fixed. Maximum value is fixed. So now at present this is 1. After that it can go up to 2. After that it can go up to 3. So this particle will get a chance to get maximum displacement. In which way? Progressive way. But here you see, if a particle is present in a particle means a particle of the string present on the string will have a constant displacement. Its amplitude is how much? This much. Lifelong this amplitude is A only. Lifelong its amplitude is A till it is in vibration. Suppose button you tegidre on the string, if you keep some cloth, if you remove one of the cloth, what happens? It starts vibrating. So continuously a particular point will have constant amplitude. But due to damping, due to viscosity of air, after some time it starts vibrating. Till then that amplitude remains same. Gradually the amplitude gradually decreases. But those points which are not at all vibrating, they won't vibrate at all. The string which is fixed at both ends, if you pluck at the middle point, those 2 points will never vibrate. But the middle portion will vibrate. Next portion vibrates little bit. Next portion little bit. Next portion little bit. Little. So lifelong in this, lifelong means during this entire vibration, these particles will vibrate only this much only. They cannot go beyond this point. Understood, students? Traveling wave, each particle will get a chance to get a maximum amplitude. But they have fixed displacement from the mean position. Artha agida illa? So what is the main difference between traveling and stationary wave? Traveling and stationary wave, main difference. In progressive or traveling wave, all particles of medium have have same amplitude. Not same displacement, same. Now 2 centimeters, then later it will become 2.2, 2.4, 2.6, 2.8, 2.10, 3, 3.2, 3.4. Let us say maximum 4. Then it will decrease 3.8, 3.7, 3.6. Then become 0. Then minus 0.1, minus 0.2, down, minus 4, plus 4 to minus 4. Once again increases, plus 4. That means at a particular time, see, this is the mean position, this is the mean position, this is the downward point, this is the upward amplitude. Now particularly when you take a photo, the particle oscillating this much. Next photo. What is the meaning of this one? It is coming down. We are taking photos continuously. Then it decreases. Then it starts going up, then coming down. Actually, everything happens in a straight line only, one line. So displacement changes from time to time, and it will get a chance to get a maximum amplitude. But in a stationary wave, what happens? In stationary or standing wave, only some particles will have maximum amplitude. Andre different particles of medium have different amplitudes. Correct? This is the maximum displacement, different amplitude. This is different. This particle has different amplitude. This particle has different amplitude. Different particles have different amplitudes. Is it clear? Understood? Now we know the length of the string. What is the length of the string here? How much? L. And what is the point here? What is the name of this point? What is the name of the point where there is no amplitude, no vibration? Can I call it as node? What is this? And what is this? Antinode. What is the distance between node to node? What is the distance between node to node? L.
Yes, sir.
But node to node distance is also equal to lambda by how much? See the students, when a wave is created, station wave, it is produced like this. So in this, if you take one wave, this wave, from crest to crest distance how much? Crest to crest distance how much? Lambda na wavelength. Crest to crest. So single wave we call it as crest, we call this as crest, and we call this as trough. Similarly, if you take the other wave, for this wave, this is the top, this is the top, this is crest. So for this wave, trough to trough distance. For individual waves, when these two combine, we call this as a antinode, we call this as antinode, we call this as antinode. So what is the distance between antinode to antinode? Is it lambda by 2? What is the distance between node to node? This is also lambda by 2. Artha aita? Now, node to node distance. How much? Lambda by 2. Now we can write L is equal to how much? And the string is said to be vibrating in its fundamental mode. Which mode? So string vibrating in one loop. How many loops are there? Only one loop. Then the corresponding frequency is called fundamental frequency. How to find frequency? F is equal to, V is equal to F lambda. F is equal to, around 2 classes back, 2 days back, we derived the expression for the speed of a transverse wave on a string. What is the formula? V is equal to root T by mu. So in place of V, can you write that formula? Because that day also I took a string, I suspended some load, sonometer, by changing the loads, tension is changing, then we found the speed of the transverse waves produced in a string. So this is equal to root T by mu by, makle, what is lambda here? Lambda here. So this is the root T by mu by. So what is the frequency of the stretched string when it is vibrating in one loop? This formula, 1 by, what is the formula? 1 by 2L root, 1 by 2L root T by, no. It should be known to us while studying stationary waves formation in different instruments. Those are terms, write down, terms related to stationary waves. The first one, note student, note down. So what is a note? Note is a musical sound. It is a note, any musical sound produced by simple harmonic motion of a source. Suppose if you take drum, when vibrating drum, so whether the layer of the drum is oscillating simple harmonically or not, yes, then the sound that is coming from the drum is called note. Second one, tone, same spelling, same numbers, same letters. Note, this is a tone. All musical sounds consists of many frequencies. Is called a tone. Students, in a song we will have a note, that is musical sound, produced from one instrument, drum. The sound coming from the drum is called note. And if you take this guitar, veena, drum, flute, all together, if all are mixed together and coming as a musical sound, then we call it as note. So note is from one instrument, tone is from many instruments. Is it clear? So what you can find in a song? Note or tone? Tone. But if you are playing guitar and singing a song, then it is called note, not a tone, because single. So here I can write single, one instrument. One instrument is note, multi instruments will give tone. Clear? Now third one, fundamental frequency. Note down. fundamental frequency. The minimum frequency produced by any musical instrument is called the minimum frequency produced, the minimum frequency produced by a instrument is called minimum frequency, is called fundamental frequency. Harmonics. Frequencies which are integral multiples of fundamental frequency. Are called harmonics. Listen students, if the fundamental frequency of an instrument is F, how much? Let us say one guitar producing 300 Hz frequency. But if you change the mode of vibration, same guitar only, if you change the mode of vibration, the 300 Hz can be increased to 600, 900, 1200, 1500. We will learn how to increase that frequency. But those are called harmonics. Fundamental frequency is called, fundamental frequency means minimum frequency, minimum frequency. What are harmonics? Double, integral multiple means 1, 2, 3. These are called integers. That is 2f, 3f, 4f, 5f and 6f, nf. These are called harmonics. What are these? Harmonics. Fifth one, overtones. Frequencies higher than fundamental frequencies. All these are overtones only. Harmonics, overtones. Next one. Unison. Listen students, two instruments are said to be in unison if their frequencies are equal. So when two instruments are said to be in unison? Two musical or any other instruments, musical or other instruments are said to be in unison, said to be unison if they frequencies are equal. If the frequencies are equal, then they are said to be in unison. Then resonance. Listen students, making a body to vibrate. What is resonance? Making a body to vibrate without applying any external force when it's a natural frequency is equal to another vibrating body. So already we discussed this previously. If I take two bodies here, two tuning forks, listen students, listen here. I have taken two tuning forks whose frequencies are same. They are identical tuning forks. Frequency of this one is F, frequency of this one is also F. But there is a distance gap between these two, and only this is vibrated by hitting this with a rubber hammer. To vibrate this one I am using external force. So now this one is vibrating. This one is vibrating like this. This one is vibrating. But the other one is not vibrating. This is vibrating on both sides. This is called handle. These are called prongs. This is handle. Those two hands are said to be prongs. So when the prongs are vibrating, and these waves will travel towards this one, direct force is not acting on this one. Direct force acting on this one. Direct force, hammer force. But this one starts vibrating even though there is no direct force acting on the second one. This phenomena is called resonance. So what is resonance? You observe this one. Making a body to vibrate. We are making this body to vibrate when its natural frequency, F is equal to another vibrating body. If these two frequencies are equal, if one is vibrated, the other one also vibrates. This is called resonance. So on day 1 I told you, students, it takes some time for you to get resonance with my class. First day my frequency and your frequency will be generally different. But with the days, my frequency and your frequency will be matched. And on that day resonance will be produced in our body, in our brain, everything. Then you will start reading physics. So that resonance is required. If the resonance is not there, just I am vibrating here and you are not responding at all because your frequency and my frequency is different. I am vibrating with my frequency and you are not vibrating because the frequencies are not equal. Then that vibration will not be produced in our body or in our brain, in our thoughts. So resonance is most important phenomena in physics. Then octave. Students, if the frequency of body is F and when the frequency is octave to the initial frequency, octave andre you know 8 octave, oct 8. So 8. If you see sa re ga ma pa da ni sa, sa also once again 8 only na. 8th one repeat ಆಗ್ತಾ ಇದೆಯಾ? Here also octave ಅಂದ್ರೆ ಏನು? In the music classes, those who attend the music classes, they know. In this sa re ga ma pa da ni sa, sa re ga ma pa da ni sa ಅಂದ್ರೆ the first sa with the frequency is F, the next sa should be with the 2F. It should be doubled. After the 8th one you have to increase your frequency. That is called octave. What is octave? Frequency is double to its initial value, initial frequency. If the frequency of one body is doubled, then it is called octave. What is that? Octave. The string is vibrating in one loop. String is vibrating in. So this is the actual string taken and now it is vibrating and the different particles of the string is vibrating with a different amplitude. This amplitude is always maximum and this amplitude is always 0. So then it is said to be vibrating in how many loops? Only one loop. In one loop, students, if you observe the diagram clearly, when string vibrating in one loop, point number 1. String vibrating in one loop. We have two nodes, one antinode, correct? How many nodes are there? Two nodes, one antinode. So then, how we got this formula here? First, length of the string is L is equal to how much? Lambda by 2. Distance between the two nodes. From this, lambda is equal to how much? 2 L. Then I want frequency which is equal to V by lambda. Velocity of wave, transverse wave on a stretcher string is given by root T by mu by 2L. This is 1 by 2L root T by mu. So this is the fundamental frequency of a stretcher string when the string is vibrating in one loop, and I wrote this formula here. What is the name of this frequency? This is the minimum frequency of the stretcher string. That's why we call it as fundamental frequency of stretched string. Fundamental frequency of stretched string. What is the formula? What is the formula? F is equal to 1 by 2L root T by mu. This is the fundamental frequency. When it happens, if the string is vibrating with one loop. When it vibrates with one loop, if you apply force exactly at the center of the string, either up or down, if you pluck it, then it starts vibrating with a single loop. Two nodes at both ends and one antinode at the middle. Suppose if you take the same string, students, I am taking the same string here, same string, fixed between these two ends, thickness has changed. There is no change in length of the string, and then this is the fixed end on left side, fixed end on right side, same string only, but I am not applying force on the string at the middle. I am not plucking the string at middle, I am plucking it somewhere here, 1/4 of the length of the string. Then what happens, we will see. What happens? I am plucking here, the string will come down, now we will get a wave like this. But after reflecting from this one, from rarer to denser medium, phase changes or not? 180 degrees, now it will come back. Can I say the string is vibrating in two loops now? This is one loop, this is now I am writing the equation number 2. String vibrating in two loops. In two loops, how many nodes are there? 3. 1, 2, 3. So I am writing 3 nodes. How many antinodes are there? 2 antis. So now we can write those nodes and antinodes, we can represent here. This is a node, this is a node, this is a node, and this is a antinode. But according to stationary waves, what is the distance between two nodes? 2 nodes. From here to here, lambda by 2. From here to here also lambda by 2. So now we can write, students, what is the length of the string? Whether length is remain same or not. I am taking same string only. The only difference is point of plucking is different. Previously at middle, now at 1/4 length of the string. So what is L? Lambda by 2 plus lambda by 2. Is it 2 lambda by 2? This is lambda. Here L is equal to lambda is equal to 2L. Now lambda is equal to L when the string is vibrating in 2 loops. This is frequency 1, also called fundamental frequency. Now F2, because this vibration frequency is different than the first one. This is different. Here now it vibrates more than the first one. We will see how it vibrates. Formula V by lambda only. What is V? Tension has not changed. Same string only, not tension not changed. Same string only, mu also not changed. So what we can write in place of V? T by mu. We have not changed the tension. We have not changed the Y. Because this depends on Y only. But lambda. So now I can write 1 by L root T by mu. The same thing, students, numberally, generally we write this as 2 by 2L root T by mu. Is it same or different? Same only now. Same only now. I just wrote this one to compare this one with the previous one. So now you see this one. You see this one. Is this double to the previous one? Previously 1 by 2L root T by mu. Now 2 by 2L root T by mu. So can I write this as 2F1? This is F1, 1 by 2 root T by mu. What is F2? 2F1, 2 into F1. So this is called not the fundamental frequency. First harmonic, or generally we write this as a first overtone. What is this? This is a fundamental frequency. This is a first overtone. What is this? First overtone is double to that of fundamental frequency. Now students, I am taking the same string only. I am taking same string only, but string vibrating in 3 loops. String vibrating in 3 loops. Now we will draw the diagram. We will draw the diagram for the same string only. I am not changing the string. What is the only change that I am doing now? I will change the point of plucking. So same string, and then these are the fixed ends. This is the fixed end on other side. Instead of plucking here and here, I will pluck now here. Then what happens? This is the first wave. When I pluck this one wave, that string will come to this structure, this form. But after striking this one, phase change will take place. How much? This is the 3 loops. How many loops? How many loops are there? Now I will write notes. 1, 2, 3, 4 notes, 3 anti-notes. Okay. Now, what is the length of this one? This is lambda by 2. This is lambda by 2. This is lambda by 2. Now I will write the explanation here. So what is the total length of the string? Whether the string has changed or not? No change. What has changed? the point where you applying force on the string has changed. Previously middle, ಆಮೇಲೆ ಇಲ್ಲಿ, ಆಮೇಲೆ ಇಲ್ಲಿ. So now this length is lambda by 2 plus lambda by 2 plus lambda by 2. 3 lambda by 2. From this lambda will become 2L by 3. Here I will write lambda 1. I will write this as lambda 2. This is because wavelength is also changing. Now, what is F3? Formula. V is not changing, students. V remains as T by mu only. Same tension, same string. I am not changing the T and mu. This will become root T by mu by lambda 3. If you write this one here, 3 by 2L root T by what is the name of this one? This is a fundamental frequency. Fundamental frequency. When the string is vibrating in one loop, this is called first overtone and this is called second overtone. And can I say second overtone is 3 times the fundamental frequency? So what are the ratio of frequencies in a stretched string? Ratio of frequencies in a stretched string. This is a fundamental, this is a first overtone, this is second overtone. In all these three formulas, 1 by 2L root T by mu constant. Here we have 1, here we have 2, here we have 3. Remaining everything same. So answer 1 is to 2 is to 3. The fundamental frequency of a stretched string. Formula: fundamental frequency of a stretched string. How much? F is equal to 1 by 2L root over T by mu. Correct? ಇದೆನಾ? So in this case, students, if you take this formula, F is equal to 1 by 2L root T by mu, we can compare the fundamental frequency with length, the fundamental frequency with tension, the fundamental frequency with mu, because 1 and 2 are already constants. So the fundamental frequency of a stretched string depends on length. How? Fundamental frequency of a stretched string is inversely proportional to its length if tension and linear density are kept constant. First one. Second one, the fundamental frequency of a stretched string directly proportional to root T if length and linear density of the string are kept constant. Third law, the fundamental frequency of a stretched string inversely proportional to root mu if length and linear density are kept constant. These are the three laws of transverse wave. What are these three laws of transverse wave? So what is the first law of transverse wave? First law of transverse waves. These are transverse waves or longitudinal waves? So first law of transverse waves on a stretched string. So I'm writing the statement, you just see the statement. What is it F there? Is it first overtone, second overtone or first fundamental frequency? Fundamental frequency. So I'm writing the fundamental frequency of a stretched string is inversely proportional to its length. Inversely proportional to its length. Inversely proportional to its length. When if tension and linear density are kept constant. The same thing, this is statement. I will write this statement in the form of an equation. So what you can write? N inversely proportional to L if T and mu are constant. This is the first equation for first law. So N is equal K by L. N is equal to K by L. From this NL is equal to K, or this can also be written as N1 L1 is equal N2 L2. What is this? N1 L1 is equal to N2 L2. So this is the first law of transverse waves on a stretched string. What is this? First law of transverse waves on a stretched string. Now, second law. What will say? Second law. What is second law? F directly proportional to root T if L and mu are constants. So I am writing second law of transverse wave. On a stretched string. I am writing this. The fundamental frequency means the minimum frequency, right? This is the minimum frequency. Next one, first overtone, second overtone, third overtone, fourth one, so on. So the fundamental frequency of a stretched string is directly proportional to what? Directly proportional to square root of tension if length and linear density of the string are kept constant. Kept constant. Now I will write the same statement in the form of equation. What is that? N directly proportional to root T if L and mu are constant. From this, N is equal to K root T, or directly I am writing N1 by N2 is equal root T1 by T2. T1 by T2. So this is the second law of transverse wave in a stretched string. Students, what is the third one? Fundamental frequency of a stretched string is inversely proportional to square root of the linear density if length and tension are kept constant. That is third equation. Third law I am writing. Third law of transverse wave on a stretched string. So statement, you can write the statement now. the fundamental frequency of stretched string, you can write now in our notes, is inversely proportional to square root of linear density if the tension and length are kept constant. If tension and length are kept constant. So we can write n inversely proportional to root mu if L comma T are constants. We can write n is equal to k by root mu, which can also be written as n1 by n2 is equal root mu2 by mu1. We have two problems based on stretched string, students. The first problem, a string of 7 meters length has a mass of 0.035 kg. This is the length of string L, this is mass of string M. If tension in the string is 60.5 newtons, while reading the question sometimes some students they may read this as a 0.65, be careful, okay. Then the speed of a wave on the string is dash meter per second and the frequency of second over tone is dash hertz. Now first one, what is the given data? Length is equal to 7 meters, total mass of the wire is equal to 0.035 kg. To solve such problems, first we need linear mass density. What we need? So how to find linear mass density? Total mass of wire by total length of wire, 0.035 kg by 7. Now this can also be written as 35 into 10 power minus 3 by 7. So 5 into 10 minus 3 kg per meter is the linear mass density. Now I want first we need speed. What is the speed of a string wave produced on a string? Speed of a transverse wave produced on a string is root T by mu. What is the tension in the string? 60.5. What is the linear density? 5 into 10 power minus 3. So you can write this as root over 60.5 by 5 into 10 power plus 3. This will become 5 ones, 5 12s, 50, 1 2 1 into 10 power 3 under root 121 into 10 square. Root 121. Root 10 square. So what is the speed of the transverse wave produced here? So the first answer for this one is 110 meter per second. Second one, we need frequency of the second overtone. Frequency of the second overtone. First let me find out frequency, fundamental frequency of the transverse wave produced in the string. What is the fundamental frequency? It is not asked, but I am finding fundamental frequency. F is equal to 1 by 2L root T by mu. Students, we know this value. This is 110. This is the speed, just now we found this one. So the fundamental frequency is 1 by L. but this is into 2. This is a 2L students. Into. So this is 110 by 14 hertz. This is the fundamental frequency. I need second overtone. So what is first overtone? F2 is equal to 2F1. This is how much? 220 by 14 hertz. Now I need second overtone. Second overtone. This is F3, which is equal to 3F1, because the ratio of the frequency is 1:2:3. So this will become 330 by 14 hertz. How much? 330 by. So directly I am writing this as 330 by 14. Otherwise you can simplify this. Further you can simplify this. This is a 2 sevens to 165. You can also write this as 160 by 7. Further also you can do it. 7 ones, 7 twos are 14, 15, 16, 25, 7 threes 21, 40, 7 fives. So this is nearly 23.5 hertz. This is the first problem. Second problem, students. Second problem, we are solving this problem similar to the previous one, slightly different. A stretched string resonates with a frequency of 512 Hz and the length of the string is 0.5 meter. There is a stretched string, students. This is a stretched string. Resonance with a tuning fork. There is a tuning fork here. What is the frequency of tuning fork? 512 Hz. This is the frequency of the tuning fork. It is resonance with the, resonance means both frequencies must be same. So this is the tuning fork frequency. I will write this as Ft. What is Ft? Tuning fork frequency. What is the frequency of the string? 512. 512. And here it is resonating with something, but with what frequency they have mentioned? Always you consider the fundamental frequency. So for this string, what is the fundamental frequency? 1 by 2L root T by mu is equal to 512. Equation 1. Equation 1. Now, the length of the string required to vibrate with a tuning fork of length 256. Now I have taken one more tuning fork whose frequency is, what is the frequency of the tuning fork now? 256 Hz. Frequency reduced. Now I have to take one more wire whose frequency must be equal to how much? How much? 256 Hz. Students, here frequency reduces. Here also frequency reduces. When the frequency reduces, length increases or decreases? We know this formula. F is equal to 1 by 2L root T by mu. I am not changing T and mu in this problem. I am changing only the length. So frequency reduced means length. So that's why see the diagram. I have drawn a bigger line here. Reason? Length must be more. By checking the options itself, if one of the option is more than this 0.5, that is your answer. But here options are not there, we have to solve this problem. Now, what I am going to write now? 1 by L2, this is L, root T by mu is equal to 256, equation 2. Equation 2. So can I cancel these two now? What we can cancel here? Root T by mu, root T by mu cancel. 256, 1, 2, so 2 sir. 2 get cancelled. So this is 1 by L2, never there. L2 by L1 is equal to 2 na? 2 by 1 is 2. I want L2. So what is L2? 2. L1. So what is L2 here? When the frequency is halved, ಹಾಫ್ ಆಗಿದೆಲ್ಲ, ಲೆಂತ್ ಶುಡ್ ಬಿ ಡಬಲ್. ವಿತೌಟ್ ಸಾಲ್ವಿಂಗ್ ಪ್ರಾಬ್ಲಮ್ ಆಲ್ಸೋ, by just memory, with the common sense, without solving this, we can say first frequency 512, second frequency, and according to the formula F is equal to L, frequency how? Length? Answer 0.5 into doubled, 1 meter answer. This is without solving the problem. Students, if you take veena and guitar, and we are using same wire in both, we are using same wire, which gives more frequency? Guitar. Veena length ಜಾಸ್ತಿ, frequency ಕಮ್ಮಿ. Guitar length ಕಮ್ಮಿ, frequency ಜಾಸ್ತಿ. Veena guitar